So I would like to tell you about Affirm. So we are a fintech startup, and we have a delightful mission of delivering honest financial products that improve our consumers' lives. Now, how do we do this? One of our most popular products has been to create a simple way to offer honest consumer financing at different various merchant point of sale systems. So looking at it, we have about 1,000 plus merchants who integrate with us, and they put Affirm promo banners like this on their website, which goes to show, like, for example, there's a watch which is worth $800. You can buy it with Affirm for about $70 to $80 per month. Now that's a loan. And once a user clicks on this option or selects Affirm as a payment option during their checkout, they get sent to our page, where we take them through a very quick process of like a loan application process. So our USP there is, like, there's not much of paperwork, the decisions are in real time, and our entire flow is very intuitive, and customers get the loans almost instantaneously. Now remember this, our loan underwriting process takes seconds to do. It's not done in days. Now this puts a lot of challenge and pressure on the engineering teams to deliver this kind of performance. On top of it, our ever-growing consumer base, they love us. Our NPS scores compared to top brands is like very high, and we want to continue maintaining this. This again puts a lot of pressure on the engineering teams. And I'm going to walk through some of the performance improvements that my team has to do just to keep this kind of happiness and performance happening all the time. So the other challenges that we have are similar to all the other startups, like, which work in the same space. It's about, like, we need to ensure data security, data consistency because we are dealing with money, scalability and reliability. We have SLAs with a lot of our partners, and we need to adhere to that. People try to steal money from us all the time, so we have to ensure that we don't fall victims to fraud. We need to automate things, automating not just the infrastructure, but also a lot of our core business flows. And that is, these are the kind of business problems that my team is trying to solve. And along with this, we have a lot of legal compliance issues. And we need to keep our operational costs low because we are in the business of lending money, and we need to ensure that we are profitable. So I'm going to walk you through how our stack looked like in 2016, when when we started off, and how it has evolved into today. So our stack was kind of simple. It's a standard multi-tiered architecture where you have web servers, workers that pick up and do more CPU-intensive jobs, and then we have, like, different services talking to each other over RPC. Now, taking the simple case of a user applying for a loan, user's browser or from a mobile phone, they actually make a request to our web servers. Our web servers take the data, they don't process it immediately, they queue it up into RabbitMQ, which is an open source message queue, and then send it off into our Celery workers. Celery is a Python framework. It's an open source framework for doing task execution in a distributed manner. So these Celery workers pick up the job, and they start this complex process of underwriting, where they take data about you from our systems, they talk to different external data sources, fetch the data, munch it all together, and decide whether we can give you a loan or not. And once that's done, we actually tell the user that you have been approved, and then they go through their entire checkout process. So this is pretty like a simple service, and we also have some batch jobs that used to do taking payments from the user and do a simple money movement. And then what happened was we ran into scale. We had more merchants. Our product was popular, more customers, more merchants, and then Thanksgiving comes in when all the merchants see spikes in load, and that started putting in a lot of pressure on us. So how did we go about solving this? We decided that we are going to instrument our clients and servers very heavily. And we started off by setting our 3 big goals for our instrumentation infrastructure. That is observability, reliability, and usability. We should be able to observe anything that is happening within our platform, anything that is happening within our users in a reliable manner, and all the metrics that are being generated should be usable. So let's look at the server instrumentation stack. We started off with we have different Python frameworks that we use, like Flask, we use Celery, and we use Luigi. So we started hooking metrics into these frameworks. So any endpoint that one of our developers launches, it's automatically measured. Any Celery task that a developer added, it's automatically monitored. We also have different systems that collect metrics about our infrastructure, like EC2, RAM, CPU, DB capacity, and things like that, and feeds all this into Riemann. Riemann is an open source stream processing system, which is good for sending out large amounts of metrics. So Riemann would take this metrics, batch it up together for 10 seconds, and then write it into this open source time series database called InfluxDB. And we had Grafana, which we used it for visualization, and we used Cabot, which is another open source tool for alerting on any anomalies. Like if our HTTP endpoints were generating 500s, we would get alerts automatically. So this is how our stack was. And these are some of the examples, like how every engineer gets this for free. Any code that they add, these are the different framework metrics that get added. We also expose our metrics library to our developers where they can add custom metrics. So if they have a specific flow, they can add custom metrics and instrument what is happening with their code in production. This was good, but again, growth happens. We ran to a point where we started generating almost 500 million metrics per day just for our online loan servicing service. And developers started adding a lot of attributes into metrics which would help them slice and dice and visualize it better. This added more pressure. We had to, like our existing Riemann servers were not able to handle the load and we had to scale it up. And InfluxDB was just not keeping up with the load. It would fail all the time and my team was spending a lot of time in maintaining and running InfluxDB. So what did we do? In 2017, we actually made slight changes to the architecture. We put a load balancer, that's AWS ELB, in front of our Riemann servers, which allowed us to scale Riemann servers independently of our volume. We could also do auto-scaling at this point, which kept our cost low. And we replaced InfluxDB with Elasticsearch. Why Elasticsearch? Mainly because my team had experience with Elasticsearch for the last 5 to 6 years. We have been working with it even before version 1 came out. And we were very confident about scalability of Elasticsearch. But Amazon also launched AWS Elasticsearch, which was a hosted version, which meant that my team did not have to spend time in maintaining another time series database. So we moved to this infrastructure and it worked really well for us. And it kept us going for a year. But then, engineers, developers, they want more features all the time. So they started asking like, oh, give me ratios on metrics. I need ratios of 500s to the total count, grouped by 2 minutes, 5 minutes, 20 minutes. Yeah, and they asked for that. It's valid. The reasons are very valid. They wanted metrics enrichments. They wanted, okay, if you have a merchant ID, we want to replace it with a merchant name so that our dashboards are more meaningful. But for my team, metrics infrastructure at this point was very critical. The time between emitting a metric and it being available for visualization was 10 seconds, and we did not want to cause any delays in this. What did we do? So we started sending the metrics to Riemann, and along with sending it to Riemann, we actually piped it out and started sending it into Kinesis streams. So Kinesis is an Amazon product which is like hosted Kafka almost, and it was really good for us. And we used this tool called Kinesis Analytics, which allowed us to run SQL-ish queries on our metrics infrastructure, and we started generating ratios, we started generating more fancier metrics on a separate stream, and we would feed it back into Elasticsearch. So we had a different SLA for this service, and whatever happened, we would not bring down our core metrics infra. And we were able to launch like ratios for our core framework metrics in 2 weeks. So this just goes to show that this is infrastructure that we did not have to manage, and we just made use of what AWS gave us. So what did we learn from this? One is like decouple systems. Ensure that any component in your architecture can be scaled independently and be replaced if required. Try not to maintain infra. My team, I want them to be in the business of building products, building solutions that are useful for the company, and not in maintaining InfluxDB or another database. So we try not to build it. And we also started talking to AWS more. We told them that these are the issues that we are facing. We got hooks into AWS roadmap, which helped us plan and prioritize our feature development. So yeah, this is working really good for us. Now let's look at how client instrumentation happened. Again, going 2 years ago, we had a similar stack, but instead of Riemann, we actually put out a load balancer with Nginx nodes behind it. And our client libraries like JavaScript and iOS, Android libraries would send events formatted as JSON. They would just post it into our Nginx instances. We would log the data into access logs. We would tail it and send it off to SQS, and then use the standard ELK stack, Elasticsearch Logstash Kibana, and to get the same visualizing and alerting that we needed. This was working well for us 2 years ago. But again, growth happened. Our volumes grew so high, and every engineer wanted to like instrument every part of their stack, the front-end stack. That was adding a lot of pressure on the systems. We ran into high cost of SQS and Redshift because we were storing the data in Redshift, and it was used by our analytics teams. Our engineers added like 100 plus attributes to each metric, and that was turning out to be a problem for Elasticsearch. We were running with HTTP 1.1, and that gave us a lot of heartburn. I'll give you a case study of how we solved that. And again, we started getting more feature requests. So before I go on, let me tell you about how HTTP 1.1 was an issue for us. So this is how a normal merchant would work. Like they would have a product page, and they would have a single buy with Affirm button, and this would make an API call to our server, and like we would have tracking on this. This was good. Each API call would take about a millisecond, and that was good for us. But some of the other merchants, like the bigger ones, they had 70 products listed in a page, and they would make this call for each product. They would make a call to our server to get a calculated value. Now, the way HTTP 1.1 worked, the browsers would open like 5 or 10 connections in parallel to our servers and would make these API calls in parallel, but in batches of 5 or 10. Now, this resulted in each row of this merchant page loading up slowly. You could actually see it getting rendered one by one or row by row. So we did not know this till a merchant complained to us. And then we realized that we were causing bad users were feeling bad about this whole slow page loading. And yes, our mission is to keep customers happy. So we started looking at solutions. HTTP 2 was a solution. You could actually, with connection pipelining, you could make multiple requests over a single connection. So we started exploring like how do we launch HTTP 2 in our systems. We looked at Nginx and looked at other open source modules. Thankfully for us at that point, Amazon launched CloudFront with HTTP 2 support. It was perfect timing for us, and we wanted to switch to it. But I did not want to take a full switch, like 100% switch to HTTP 2 immediately. I wanted to like gradually roll it out. So Route 53 helped us with it. Route 53 has added a lot of advanced traffic shaping abilities. So we were able to send a small percentage of the traffic to CloudFront and keep most of the traffic going to our older servers, experiment with it, and within a week, we could actually ramp up our entire traffic to HTTP 2. So this is how our stack looks now. It's Route 53 sitting there, sending almost 97 to 99% of the traffic through CloudFront to our load balancer. And like we still have some experimental traffic going directly to our ELB. The stack was the same. But again, if you notice, we replaced SQS with Kinesis, Kinesis Streams, Kinesis Analytics, and we also replaced the logs going into Redshift. We started sending it into S3, and we use Redshift Spectrum to store data into Redshift. So this worked out well for us. Our performance was really good. The moment we launched, we could see that our merchant pages would get loaded in almost like a jiffy. And that itself was a big boost for us from our merchants, and our entire stack remained the same. At this point, we also noticed that our West Coast, our infrastructure is on East Coast. We noticed that our West Coast customers were facing about 50 to 100 milliseconds latencies and getting the data to us. So what did we do for that? We launched more services in West Coast, and we use Route 53 and CloudFront just to front our entire service, and we reduced this latency. So overall, our entire instrumentation effort has been like really good, and it's working out well for us. So again, from the client instrumentation side, what did we learn? One is to reuse technology. We reuse the same stack that we have for our server instrumentation. We use that for client instrumentation. We realize that we have to be relentless in measurement. There are things that always keep looking for what we are not measuring. Measure it and improve it. And if required, fix it at some point. And another thing we realized is Amazon is going to beat you to infrastructure development. Do not try to build your own infra. Do not try to maintain it if Amazon is doing it. They'll have more people. They'll do it faster than you, for sure. So let's look at how we now, looking at our instrumentation stack, let me walk you through how we brought some of this knowledge into our core stack. We replaced our traditional RPC system, which was based on zero RPC. We replaced it with HTTP, we load ELBs, Route 53, and using Route 53 health checks, we were able to modernize our RPC infrastructure. We brought the same like ELK stack and Amazon's Elasticsearch Kinesis infra and started using our logging infrastructure. We had security issues where we could not send our logging data to like Splunk or some other service. So we had to build it on our own. And we were able to do that very easily with AWS. We started putting CloudFront with web application firewall on front of all our services. And we are building out our multi-region strategy for our core services using the same stack and lessons that we learned from our instrumentation stack. So the last 2 years, we actually adopted a lot of Amazon components. Like we were running our own EC2 instances as NAT gateways. We moved over to Amazon's NAT instances. We used S3 cross-region replication and a lot of other tools. I'll actually walk you through 2 of these case studies, which are interesting. But before that, a recap. This is how our stack looked like 2 years ago. This is how it's looking now. A key point to note is that our core functionality in our stack has not changed. We still have web servers, we have workers, and we have our RPC systems, but we have replaced and modernized a lot of our stack, and most of them are now AWS managed stack. So we just started getting out of the business of maintaining low-level infrastructure. So let me end my talk with 2 case studies. So one of our case studies is how we are scaling up our batch job infrastructure. If you look at the slides before, we had our batch job infrastructure as a small block there because we started off with running just 4 or 5 batch jobs. But that's not the case now. As I told you, we are trying to become a financial institution and lending lots of money. This is how our bank engineering stack looks like. It's an extremely complex project with money moving across the stack. And our infrastructure, the batch job requirements became so complex that we had to over-provision a lot of infrastructure, which resulted in wasted capacity. There were times when multiple jobs would run at the same time, and that would result in resource contention, like read replicas, hitting read replicas. And we are looking at how to solve these problems. Some of the jobs are so complex, we had to run them in production in a blue-green mode for many days before we could promote them into production. So how do we do this? We started looking at different kinds of ways to solve this problem. But again, we realized that we can reuse a lot of AWS technology. For example, Aurora read replica scaling. We migrated all our MySQL instances to Aurora, and Aurora now supports read replica auto scaling, which means if there are multiple jobs that suddenly hit a read replica, Aurora can scale up and handle it. Again, we don't have to manage this. DB cloning. When a developer wants to launch a blue-green mode of deploy, we are able to clone our production database in seconds and give them access to a cloned DB where they can run their code, validate it, and then eventually when they're happy with it, we can promote it. How are they happy with it? They have metrics for measuring how good the thing is working. So we are able to do this, and again, my team is happy with the DB cloning functionality. Labs mode. How many of you have run into schema migration issues with large databases? Like if you have 1 billion rows and if you have to add a column to the table, almost always end up with downtime on MySQL. Or you end up looking at tools like Percona, Toolkit, and other open source solutions to make this happen. But we enabled Aurora Labs mode on some of our non-critical databases, and it's been a lifesaver for us. And now we are also looking at Fargate to auto-scale our compute infrastructure. So this just goes to show that we don't want to get into the business of maintaining complex database technologies and just rely on Amazon to go ahead and deploy business solutions. Another case study is a slightly different one. It's more about security. So we had, as you run startups, you will know that you want to use a lot of external services for some of your subdomains. For example, we have affirm.com, and we have something called blogs.affirm.com, which could point to a hosted WordPress site somewhere. And you don't want to maintain that. But hosting a subdomain is always risky. The reason is, if your affirm.com application sets a wildcard cookie, a user logs into our site, and if they then go to blogs.affirm.com, they are sending the cookie to an external party. If the WordPress site is compromised, the cookie gets leaked, and they can then use their cookie to log in back to our service. It's extremely dangerous. We had to enable HSTS, which means all our subdomains had to have SSL on them. But for this, you have to give your HTTPS certificates to external parties. Once your cert leaves your network, you can never be guaranteed of its safety. And we also wanted to see what kind of traffic was going into our site, into external subdomains, and we did not have any visibility into that. And because of this, we were pushing back on product ideas where we were saying, okay, don't launch subdomains, launch URLs and some blogs, affirm.com/blogs, etc. But we had to solve this problem. The way we did this is we actually run CloudFront as a proxy. as almost like a forward proxy at this point. Sorry, as a reverse proxy. So you have CloudFront sitting there. We sent all our blog, like subdomain DNS entries are resolving to our CloudFront proxy. And we have AWS Lambda at Edge. Lambda at Edge allows you to write JavaScript code which runs on CloudFront Edge nodes. So any request that gets terminated on CloudFront, we are able to do almost like vhost like matching. If the domain is blogs.affirm.com, proxy it off to xyz.wordpress.com or something like that. But we also have additional code there which strips out the cookies. So we don't send our service level cookies to any external site. And we also get logs. We have excellent logging now to see how our cookies are going across various services. Once we did this, we actually launched 6 subdomains in the last quarter. Our teams, marketing teams, and our technology communication teams are very happy with us because we don't care. You can launch any subdomain because we have an infrastructure for doing that. So what we learned from this is use your non-core systems to experiment. Like you may have things like blogs and whatnot. Use new technologies like Lambda at Edge, experiment with this, and once you are comfortable, bring that back into production. Now, adapt your infrastructure. Like Amazon and other people, there are a lot of open source tools that keep coming out. Be ready to adapt and try to deprecate most of your infrastructure as soon as you don't need it. And get your teams to start building more products and rather than maintaining infrastructure. And this keeps our teams also happy because they are doing more challenging business solutions.